In this lesson, I cover Stack Overflow. It is a nasty problem when it occurs because the effects of it are so random. The system often just starts acting strange. So of course you don't want it to occur, but if it does occur, you want to take action. So let me quickly go through an outline of this lesson. I start with an introduction, like what does Stack Overflow mean, and then go through some techniques to address Stack Overflow, and these are the techniques we'll explore in this lesson. Next, I'll discuss the Memory Protection Unit, or MPU, that is becoming more common in microcontrollers. Then I'll talk about adding a stack guard using a MPU. Following this, I'll talk about a well-known technique to determine how much stack you're actually using. Then I'll look at the implementation, the code that implements these features. This is followed by a demo. And then finally, some prompts or questions for you to consider, and I'll give you my take on them. The stack is a region of RAM used for functions and interrupt handlers for temporary storage. For functions, the stack is used for things like return addresses, saving registers, and particularly local variables. In some cases, the stack is also used to pass arguments to the function, but CPU registers are used for argument passing when possible. Now, interrupts use the stack in much the same way as functions, although there are no arguments to pass. In some systems, there is a separate stack for interrupts, but in this course, we have a single stack. So as function calls and interrupts nest, the stack grows. So here we have a scenario with a function call stack that starts with main, and then main calls func2, or func1, and func1 calls func2, and while func2 was executing, an interrupt occurred. So we have this interrupt handler, and it called func10. So we want to see how this scenario is handled on the stack. So over here, we have a diagram of RAM. Now, this diagram is not to scale at all. And in particular, this bottom region here should be much, much bigger. But of course, I have to fit it on the page. So on the left is the starting address and the ending address of RAM. And this is for the MCU I'm using for this course. And you can see that the stack pointer is initialized to the highest address in RAM. And this arrow here shows how the stack grows as it's used, and the stack pointer moves to lower values as it's used. And you can in fact see here is the current stack pointer. So we can see how each function uses a bit of the stack, and as functions call each other, the stack grows, and then when these functions return, the stack shrinks. Now when an interrupt occurs, the interrupt handler needs stack as well, including the functions that the interrupt handler calls, like func10 in this case. And here you see we have some unused stack space. We need to have some spare. And beyond this, we have other users of RAM, like global variables or the heap. So the problem becomes if the stack ever extends into this area, and which is why I have this danger sign here. This is called stack overflow. Now the CPU doesn't know it's exceeding the stack area in general, and you as a developer will probably not be aware of it at first. But what happens is this memory will start to get modified at random, and usually weird things will start to happen with your system. It can be very confusing. I and many developers have spent quite a bit of time debugging a system that is doing weird things before realizing, oh, the stack has overflowed. So of course you need to make sure your stack is big enough so this doesn't happen. But as I state here, it's hard to estimate the maximum stack size because you would really have to understand the code very well and how much memory or stack each function is using. It would be extremely difficult. Now there are some tools that help you. The compiler knows how much stack each function uses, and the compiler knows which functions call each other, so it can try to figure out a worst case stack usage. But there are limitations to these kind of tools, and I really haven't used them. So here are some techniques for addressing Stack Overflow, and this is what we'll be exploring in this lesson. First, for MCUs that contain a memory protection unit, or MPU, it is possible to put a stack guard region that limits stack growth to its allocated area. We'll talk about MCU shortly. As I had mentioned, it's hard to estimate maximum stack usage. But if we can find out the maximum amount of stack we have used on a running system, it will give us some idea. So we can use this technique listed here. We fill the stack memory with a special pattern during initialization. And then as the stack is used, it will overwrite that special pattern with real data. So at any time, the high water mark of the stack, meaning the most stack we have ever used, can be determined by finding the first location not containing the special pattern. Now, this method has limitations because you often can't be sure that the maximum stack usage scenario has occurred, but it still provides a useful data point. So now let's talk about memory protection units, or MPUs. First, let me say, don't get an MPU confused with a memory management unit, or MMU. An MMU is used to support virtual memory for operating systems like Linux. Most MCUs don't support virtual memory. So an MPU is a hardware device within the MCU that can place restrictions on specific regions or blocks of memory, like whether the memory in that region can be read or written. There are a limited number of memory regions supported by an MPU, and there are 8 for the case of this MCU, which is the one we're using. To set up an MPU region, you specify a starting address, a size or ending address, and then the access restrictions, for example, whether the memory is read-only. So to create a stack guard with an MPU, you use the MPU to create a small memory region just beyond the stack area that is read-only. For the MCU we're using, the minimum MPU region size is 32 bytes. I mention this size because this is usually wasted memory. In this case, 32 bytes is not too bad. So what happens if the stack overflows and the stack guard region is hit? Well, when the processor tries to write to a location in the stack guard region, a fault occurs. And for our MCU, the fault is called memmanage. And when this happens, the corresponding exception handler or interrupt will be invoked. Typically, it depends on the software, the MCU software will do a reset. And that's not great, but it provides some things. One is safety. The reset prevents dangerous behavior due to the memory corruption. And 2, availability. We want to maximize the time the system is running properly. The idea is usually that if the system is corrupted, you just want to do a reset and get it over with. Obviously, you want to catch these problems during testing before the system goes to the field, and you want to size the stack area bigger than you think you will need as a safety margin, just in case. Usually, if there is spare RAM, you give all of the spare RAM to the stack. So here are some diagrams showing how the stack guard region fits into the RAM memory map. On the left is the initial RAM map for the course project. This is based on the linker script that the IDE generated, and we'll be looking at that linker script shortly. So the linker knows how much memory is needed for the .data and the .bss sections, because that's just based on the number of global and static variables and their size. Then there are project settings for the heap and a minimum stack size. So that brings us up to this point in terms of the amount of RAM we need. And if there is not enough RAM to get to this point, that's a linker error and the build fails and things stop right there. But in our case, we have some extra unused RAM, and the linker script and the startup code is set up to just give any unused RAM to the stack. In the case of our project, there's a lot of unused RAM, so the stack is quite large. Now on the right is a modified RAM memory map, which I got after modifying the linker script. So all I did is added this extra block here of memory for the stack guard, and this happens to be 32 bytes long. Of course, I'll need to write code to set up the MCU for this block and make it read-only. So if the stack is growing and heading this way and hits this stack guard region and tries to write to it, we'll get an exception, and that prevents the stack from corrupting these other memory areas. Now let's look at the linker script. This is a generated file in the project workspace, and you can see the file name up here. I just made a few changes to allocate memory for the stack guard region. So the first thing I did is right here, and this is just defining a constant. This is the MPU minimum block size set equal to 32. As I mentioned, for our MPU, the minimum size is 32 bytes. And then the next thing we want to look at is allocating RAM. And we're getting close here. Here it is. So in this block, it's allocating space for both the heap and the stack. And the lines that I modified or added are right here. So if we look at this existing code, this line allocates space for the heap. And in this linker script, the dot represents the current address. So we are allocating things to RAM. So this would be the current address in RAM as we allocate memory. And by adding the min heap size, we move the current address up by that much, and we've essentially reserved that memory. So the first thing I do after that in the new code is I use this align directive. And what this does is it takes the current address, this dot, and ensures that it's on a 32 byte boundary. It might have to add no bytes, or it might have to add 24 or whatever. And that's a requirement of the MPU that this block be on a 32 byte boundary. Then the next line I want to mention is 178, and this is where we add the MPU min block size to the current address. So there we're allocating or reserving memory for the stack guard. And then right before and after this, you see where we declare two variables, the start of the stack guard and the end of the stack guard. And we assign these to dot, which is assigning them to the current address being allocated. These are like global variables in C, and they are available from C language files, and we'll be using those. So after we allocate that, then the next thing that happens, this is existing code that allocates RAM for the minimum stack size. And that's the end, nearly the end of this file, and it's the last part of it that allocates memory to RAM. Now, one thing you'll remember what I mentioned previously is that the startup code will actually use the highest RAM address as the initial stack pointer, and thus it gives any unused RAM to the stack. So here are some more diagrams showing how we determine the max stack usage on a running system. It's pretty simple. During initialization, we fill in the stack with a fixed pattern, and you'll see this when we look at the code. And on this diagram, I represent the fixed pattern by this yellow with this texture. Now, as the stack is used, which it starts up here, it will overwrite that fixed pattern with real data, which is almost certainly different from the fixed pattern. And I show the part of the stack that was used here with a different color and a different texture. Now, the stack grows and shrinks as the software runs, but when the stack shrinks, the fixed pattern is not restored. It will remain whatever data was on that stack, how it was being used. And so this leaves what we call a high water mark in the memory. So you can always tell what part of the stack has not been used. So to determine the amount of unused stack, we just start at this point down here, and we just search upward until we find memory that does not contain the fixed pattern. When we find that first memory, we know we are at the high water mark, and we can calculate the amount of stack that was used. It's as simple as that. So now let's look at some code. I didn't think that these stack features were large enough for a module of their own, so I put them into the fault module. So we're going to be looking at selected pieces of fault module code. And there's no API specific to these stack features, so there's no need to look at a .h file. So we are in fault.c, and I'll show a few highlights. Starting on line 64, here is the pattern that we write to the stack on initialization. And it doesn't matter too much what this pattern value is. You don't want it to be a common value like 0 or probably any small integer. People often like to use patterns so that if they see a hex dump of memory, they can recognize it, and that's what I did. This pattern, if you read it, you can read it as cafe bad. So it's sort of a memorable pattern. Probably isn't going to happen by chance. So now we move down to, let's see, line 253. And this is fault start. This is the standard API for how modules get started. And the things that are interesting here are first here's where we fill in the stack. So the stack is being used as this code runs, and of course we can't fill in the part of the stack that's in use. So we start with the current stack pointer and go from there. Now, how do you get the current stack pointer? There's different ways. What I have chosen is to use an extension to C that's in the GCC compiler that allows you to put assembly language instructions in your C code. And this is a common thing if you want to get registers, for example, and the stack pointer is a register. So what this line does is writes an assembler, I think maybe 2 lines of assembly, that take the stack pointer register and copy it into a C variable in this function called SP. Now for this CPU, you always decrement the stack pointer before writing a value. So I decrement the stack pointer here before I write the first pattern. And then this is the loop that writes the pattern. And you can see it's comparing the stack pointer value with this start guard, which if you'll remember comes out of the linker file, and this is the start of the guard region. And so we're not only filling in the stack, we're actually filling in the guard, the stack guard as well. And no particular reason I'm doing that. I can because we haven't yet set up the MPU. So that's what we're going to do next. And now this code supports a number of different MCUs. They're all STM32 MCUs. But not all STM32 MCUs have the same MPU hardware. There's different types. And so the MCU we're using has an MPU type 1. That type 1 is just my designation. And I'm going to just quick switch back to config.h. Config.h is a huge file full of tons and tons of hash defines for different feature constants and so forth. And there's one section of it which sets a lot of things based on the MCU. So this is our MCU type, and here's where we set the MPU type to 1. So whenever I want to support a different MCU, I have to sort of discover, is the MPU the same as one I previously support, or is this yet a new style of MPU that I'm going to have to write more code for? So going back here, we have, in this case, MPU type 1. And then in this case, because this is a little bit tricky, I wrote notes about all of the things we set in the registers and what I set them to and why. And the key things are the region. This is the MPU region. It supports 8, numbered from 0 to 7. This is the starting address of the region, which again is that variable that comes out of the linker script. This is the size of the region, 32 bytes. And then this is the permissions of how you can access this memory, and this is saying it's read-only, so you can't write to it. And then I won't go through the rest of these. It's more details that are less interesting. I would suggest if you're interested in these MPUs, you look at the reference manual for the MCU, and of course I spent a lot of time looking at that reference manual, reading the details of these registers. Because these LL function calls, all they're really doing is taking this data and writing it into a register, or maybe two registers. So here we set up the region, and then the last step is we enable the MPU, and the stack guard is now in place. So there's one more piece of this code I want to look at, and that is this handler function for the console command fault status. And so this is a function gets called if you type in fault status at the console. And the part I want to look at relates to the stack. There's a print here that's just writing the limits of the stack. So the beginning address and the ending address. And that's really information that's determined at build time. You could look in the .map file and find that same information. But the more interesting thing is to find out how much stack you've used, and this involves finding the high water mark, as we call it. And so that's what these 3 lines of code are doing. They are starting at the lowest address of the stack and moving up and looking for the first place where the stack does not contain that init pattern. If it doesn't contain the init pattern, we fall out of this loop, and now we can print how much stack is being used. And so that's the whole point of using that pattern, is we can now run the system for a while and print this information, and we'll be doing that in the demo. There actually is one more thing I want to show you, I forgot, and that is another console command called fault test. And in fault test, you give it some kind of operation you want to do. And there's to test different things. And one of the operations is to cause stack overflow. And here is the code that detects that. It just calls a function called test overflow stack. And this is a simple function. It just calls itself. So this is going to be infinite recursion. So every time it calls itself, it's going to use a little bit more space on the stack. So from a human perspective, it will almost instantly cause stack overflow. And we will do this during the demo, and you can see the effects of that. So now for the demo. What you see here is the temp hum module printing out samples on the console. So first I'm going to reset the board, pushing the reset button, and then I'm going to do a Control L to stop the logging. So the first thing I want to do is look at stack usage, and that is shown on the fault status command. And you can see right here the high usage mark, the high water mark, is 864 bytes. Now I'm going to enter some console commands that I know use a little bit of stack. One is tty status. Well, let's look at the fault status again. Okay, so it's the high water mark has went up to 940, and now I'm going to do a dio status port A. I think that he uses even more stack. So we were at 940. So now we're up to 1012. Of course, if we do a TTYS status, which uses, I think, less, that shouldn't affect the high water mark, and it doesn't. So that's the usage of the stack usage, and I think you could see that if you're developing a system, you would let it run for long periods of time and enter that command and see how much stack you've used, and that gives you a sense of add some safety margin to that maybe, and gives you some idea of how much stack you should reserve. So now we're going to do a stack overflow, and that uses the fault test command, and in particular it uses this one. If you remember, we just looked at the code. When I execute this command, it's going to go into an infinite recursive function call that will quickly run out of the, quickly exceed the stack. So here we go. And that didn't take long. The system reset. So right here you can see that it reset. And before that, the fault module caught a fault, an interrupt, and that's what this fault type 2 is telling us. And then 4 is the type of interrupt, which I believe is a mem-manage one. So what I'm going to do is take this data that the fault module produced, and we're sort of jumping ahead a little bit here, and I'll run that through the decoding tool, and we'll take a look at it. So here I am in the command shell, and I'm in the fault directory, which contains the decoder tool for the fault output. And I put that text into a file called demo.txt, and there it is. So now I want to run the decoder, which, there it is, log format. So I give the directory where it finds the source code and then the file containing the text, the raw text, and then I'm just going to put that in a file called decoded.txt. So here we are in an editor looking at that decoded file, and before I look at this I want to go to the map file for the build and find the stack guard. And here it is, and the beginning address is in RAM is 2018-20 and the end address is 2018-40. So remember those values. Now we look at the fault data, and the first thing is the fault type, which is defined in the fault header file, and this would say an exception occurred. The parameter for that type is the fault number. This is defined by ARM, Cortex-M, and 4 means mem-manage. Now, mem-manage can mean a lot of things, and that information by itself is not that useful. I mean, it's good to know, but you really want more information. Well, the designers of the Cortex-M have provides other information in the form of registers, and there's a register mmfar, I think that stands for memory manage fault address maybe, and it tells us that the address that caused the fault was 2018-38. That is in that stack guard area, so this makes sense. The other thing is the stack pointer at the time of the fault was 2018-20, right on the edge of that stack guard. So that's useful information, sort of confirms what happened if we didn't know. Now there's some information that unfortunately we don't have. One of the things that would have been nice is to know what the execution address was when this occurred. And normally we get that off the stack. When an exception happens, information gets written to the stack. But of course, in this case, the stack wasn't working because we had hit that guard area. So what we see in that guard, all the stack information actually contains that fill pattern that was written actually into the stack guard area during initialization. So here are the prompts or questions for this lesson. I'll pause here just for a second and then go through them one by one with my take. Is it possible for the stack guard defined in this lesson to miss stack overflow? In other words, not work? Well, yes, I think it is possible under the following scenario. You have a function that has a block of local variables of at least 32 bytes in length, and these variables are never written. And the 32 bytes is because our stack guard block is 32 bytes. When the function is called, that block of local variables is aligned or sort of overlaps with the stack guard region. Since no writes are attempted to the stack guard region, because it's being used to hold those unused local variables, no fault will occur. So in effect, the program has jumped over the stack guard region. Now, this is probably unlikely. Although I have to say this is used as a way to attack programs, in which case it's intentional. They actually do this. I'm thinking of in the Linux world. And a larger guard region will make it less likely, but it could still occur. Now I had this note down here to check out the GCC F stack check option. This is a option for intentional attacks. And what it does is it probes the stack to make sure that the stack is really writable and to ensure there's not a guard region that is being jumped over. I'm not sure if it would work for this small stack guard region, but it might work, something to look at if you're really concerned about this. Could you somehow keep running after a Stack Overflow fault rather than just reset, which is what the fault module does? Well, I think the answer is yes. It's possible, but it seems like it would be very difficult. The thing is that the system, who knows what it was doing when it hit that stack guard? How do you recover from that? But I thought of a couple things. One is you just reset the stack pointer to its initial value and you just jump back to main and start over. Now, what's interesting is that global and static variables would not be reset to their initialization values. And maybe this is what you would want. Maybe your code would be smart enough to realize what happened and it would try to pick up running again sort of where it left off. There's actually an interesting story about the Apollo lunar lander, which did go through resets like this. It had a system exactly as I described. It went through some resets due to some issues while they were landing, and it would just pick up and keep going. So it's a really interesting story. The other thing that came to my mind, in C there are these functions called set jump and long jump. And what you can do is someplace in your code you can call set jump and it fills out a data structure. And then later you can call long jump and you pass that data structure and it sort of magically puts you back to where you were when the set jump was executed. So you can sort of go back in time. These functions have always been a little bit dodgy. People don't really think they're safe or they should be used, but it's something you could look into. I don't know really how practical it would be. So this is the end of the Stack Overflow lesson. I hope it was useful for you, and thanks for watching.